Hello, students, and welcome to class. We're diving into chemical reactions and equations. Ever wonder why iron rusts? Let's unlock the secrets of science together. Let's get started.
To understand how matter interacts, we must first establish the scientific threshold that separates a simple physical phase shift from a true chemical reaction. In a physical change, such as ice melting into liquid water, the macroscopic state shifts as the molecular lattice expands. However, the underlying composition remains entirely intact. Every water molecule retains its original atomic structure. A chemical change, by contrast, occurs at the level of molecular bonds. During combustion, existing bonds are forcibly snapped and rearranged, resulting in the creation of entirely new substances with different atomic geometries. These transformations are strictly governed by the law of conservation of mass, which dictates that matter cannot be created or destroyed during a reaction. Because the total mass remains constant, every chemical interaction can be mapped as a balanced mathematical equation, where the reactants and products contain an identical number of atoms.
While we can observe a reaction qualitatively, modern chemistry requires a quantitative accounting of every atom involved to determine the exact scale of the exchange. For complex reactions, an algebraic matrix replaces trial and error. By assigning variables to each species and solving the system, we lock the final integers into place, ensuring identical atom counts on both sides of the yield arrow. This mathematical parity confirms the reaction is physically possible under the laws of mass conservation, providing the necessary data to analyze the specific nature of the yield. Stoichiometry provides the mathematical framework for modern chemistry. It ensures that every reaction follows the universe's strict requirements for the redistribution of mass. The first reaction architecture is combination, where two or more distinct reactants merge into a single unified product. Forming these new, more stable bonds often results in an exothermic state, where excess energy is released into the surrounding environment as heat. This brick-lime kiln represents the historical scale of producing calcium oxide, or quicklime. When combined with water, it triggers an intense exothermic reaction. The mixture boils as it releases heat, yielding calcium hydroxide, a process known as slaking. Once applied as plaster, this calcium hydroxide begins a secondary, slow-moving combination reaction, drawing carbon dioxide directly from the atmosphere. Over time, this interaction creates a hardened matrix of calcium carbonate, which forms the durable white surface seen on this plaster wall. These combination reactions illustrate how matter seeks thermodynamic stability, often resulting in the spontaneous emission of thermal energy. Decomposition is the inverse architecture. Here, a single complex molecule is forced to fracture into two or more simpler components. Because stable bonds are being broken, this is an endothermic process. It requires a forced injection of external energy to overcome the molecular forces holding the reactant together. The first energy vector is heat. In thermal decomposition, high temperatures provide the kinetic energy necessary to shatter atomic bonds. When we heat lead nitrate crystals, the energy disrupts the solid structure. The macroscopic evidence of this breakdown is highly specific. The crystals crackle as they release a dense, brown nitrogen dioxide gas. The second vector is electrical current. Electrolytic decomposition uses the flow of electrons to drive a chemical change. By passing a current through water, we can tear the bonds between hydrogen and oxygen. In this electrolytic cell, oxygen gas bubbles at the positive anode, while hydrogen gas collects at the negative cathode.
An acidic catalyst facilitates electrical flow. Stoichiometrically, because there are two hydrogen atoms for every oxygen atom, the hydrogen tube contains twice the gas volume. The final vector is light. Photolytic decomposition occurs when photons provide the energy for the chemical split. When UV light strikes a silver chloride crystal lattice, it initiates a specific atomic decay. The photons strip away the chlorine as a gas, leaving behind a deposit of gray metallic silver. This historical application was the basis of black and white photography. By controlling the photolytic decay of silver halides, photographers could permanently capture light and shadow. Across all three vectors, decomposition represents the precise accounting of how external energy forces matter to fracture. Beyond merging and fracturing, matter also undergoes structural reorganization through displacement. In single displacement, a more reactive element forcefully usurps the position of a less reactive element within a compound. Whether a displacement occurs is determined by the reactivity series. This is a rigid hierarchy that dictates which elements possess the thermodynamic potential to displace others. If we introduce solid zinc into aqueous sulfuric acid, a displacement reaction begins. Because zinc is higher on the reactivity series than hydrogen, it evicts the hydrogen atoms from the acid to form zinc sulfate. The displaced hydrogen gas is released as bubbles, which can be identified in the lab by the sharp pop sound they make when ignited. Displacement also occurs as a dual exchange, known as double displacement. This occurs when two aqueous compounds simultaneously exchange their ionic partners. For example, combining transparent solutions of barium chloride and sodium sulfate triggers an immediate reorganization. This diagram shows the simultaneous swap. The barium ions bond with the sulfate ions, while the sodium and chlorine atoms reorganize into a separate salt solution. Because barium sulfate is insoluble, it disobeys the solubility limits of the water and crashes out of the liquid as a white, solid precipitate. Displacement is a governed process. It follows a predictable elemental hierarchy and the physical constraints of solubility. Many of these architectures are actually governed by a single overarching process: oxidation-reduction, or redox reactions. Oxidation is defined as the gain of oxygen atoms, or more fundamentally, the loss of electrons during a reaction. Reduction is the reciprocal inverse, the loss of oxygen or the gain of electrons. Redox reactions function through a simultaneous transfer. In this interaction between copper oxide and hydrogen, for every oxygen atom that leaves the copper, it is immediately gained by the hydrogen. Electrons and atoms are never lost, they are simply moved. This reciprocal relationship explains why we classify reactants as oxidizing or reducing agents. The species being oxidized provides the electrons for the other reactant. Therefore, it is the enabler, the reducing agent. Conversely, the species being reduced, gaining electrons, is the oxidizing agent. This closed system of electron transfer ensures that charge equilibrium is maintained throughout every chemical exchange. The observable changes in a reaction, the heat, the color shifts, and the evolving gases, are the visible signs of a deeper, governed process. Beneath these physical observations lies a mathematically precise redistribution of atomic mass and electrical charge. Chemical equations serve as the precise record of how the universe reorganizes matter while maintaining its fundamental balance of mass and energy.